Let's start your notes for section 5.1, area and distance problems. So we're going to start the conversation just by looking at what the area problem, quote unquote, means. What it wants us to do is compute the exact area between some f of x function and the x-axis on some interval a to b. So this is a rough sketch of what we're talking about here. You have some function doing whatever. You have an interval x equals a to b. And we're talking about the exact area contained between the curve and the x-axis. All right, so if the curve happens to be, straight lines or a perfect circle, we might have geometry formulas that can help us compute that area. But if it's just a regular curve, we don't have the geometry to do this computation, but it's going to end up being a really important task. And it turns out it's something that the calculus we know from earlier in the semester is going to help us compute. But we want to spend a lot of time kind of building up where it all comes from. So that's what we're thinking about right now. So what we're going to start off doing in this section is not computing it perfectly. We're going to start by using only rectangles, because rectangles are nice, to approximate this exact area. Certainly we could use other geometric shapes, but rectangles are going to be just fine for our purposes, and eventually this will connect back to the calculus stuff from earlier in the semester. All right, so the example I'm going to talk about in this video is approximating the area under x squared on the interval 0 to 2. So you can see I have sort of a rough homespun sketch of the graph of x squared on the interval 0 to 2. Oops, label this x-axis, on the interval 0 to 2. All right, so the exact area that they want us to compute here, when I do this in green, the exact area, we're going to put kind of a hard edge at x equals 2. X equals 0 is right here kind of at the angle point. So the exact answer for the area is whatever this green area is right here. And right now we don't have a way to compute it. So we're going to do what the directions say and just approximate it. And we're going to stick to only rectangles, just pretty much for now because I said so. Okay, so the first thing we could do is kind of the most naive computation, which is just one big rectangle, just to kind of get the ball rolling, right? So I could say, all right, here's a big rectangle, this whole thing right here, right? At least for a rectangle, I know how to compute the area. So the area of this rectangle is its width, which is 2, times its height, which is 4, and I get 8, which is clearly an overestimate of the correct answer, right? But from this image, I can tell, right, the exact correct answer is some number that's probably a little less than half of 8. So it at least gives us kind of a starting point. All right, so because this is such a wild overestimate, let's stick with the same theme, but we'll try to reduce the error in our approximation. And if we can only use rectangles to do this, why don't we just use more rectangles? So I could do one rectangle at 1, and then another rectangle from 1 to 2. So if I add up the heights of these two rectangles, it'll still be an overestimate, right? Because I'm still counting a bunch of area up in these corners that aren't part of the intended area, but it's going to be a lot closer to the correct answer than this 8 was originally. All right, so the areas of these rectangles would be width times height. For this first rectangle, the width is 1, and the height is also 1. For this second rectangle, the taller one, if its base goes from 1 to 2, its width is also 1, and its height appears to be 4, the way that I've drawn it. So we have 1 plus 4 is 5. So again, 5 is still a bit of an overestimate, but we're getting somewhere. Okay, we'll do one more kind of in this pattern, and then we'll kind of get to some conclusions here. Okay, so in this next image, again, I'm starting off with the same scenario. but I'll do even more rectangles, right? If rectangles are what we're limited to using, then let's just do more of them. So instead of just 2 even with rectangles, why don't we do 4? So I'll cut at 1/2 and then 3/2, or this is 0.5 and 1.5 if you would rather. And then I'll make 4 little rectangles. So the first one will be really teeny. The next one will be height 1. And then a little taller, a little taller. All right, so now I need to be more specific about how I'm setting the heights of these rectangles, because the numbers, at least for some of the rectangles, are not so obvious anymore. So I can see that they're all width 1/4. But the height of some of them is unclear, right? I can tell this tallest rectangle on the right side still appears to be at height 4, but then like this one is really unclear. Same with the smaller one at the bottom. So we want to think a little more carefully about how I've been drawing these heights. All right, let's think about, so if this one is height 4, let's think about the next tallest one because it'll be easiest to look at. So the rectangle whose base goes from 1 to 1.5 right here. So I took the subinterval 1 to 1.5, and I took the rightmost number in it, so that's 1.5 or 3/2, and I went up to the curve and just used that height, like the height of that point, to set the rectangle's top. So the y value of that point right there is the height of this rectangle. So we want to know, what's the y value of that point? Well, if it's on the curve f of x equals x squared, and it's above the x value 3/2, then it's whatever f of 3/2 is, right? So it's 3/2 squared, which would be 9/4. And that's actually how all of these heights are being set. So even when the numbers are not nice, obvious numbers, we can still do that computation, right? So if we go back to this tall one, I chose on the interval 1.5 to 2. 2 is the rightmost number, so I went up to that point on the curve and let its height set the top of the rectangle. So this height is whatever f of 2 is, which was 4, right? So this one, this second shortest rectangle here, its height is f of 1, which is 1. And that means this last one right here, which I'll kind of extend out for clarity, it's using the point above 1/2 for its height. So its height is f of 1/2, which is 1/2 squared is 1/4. Okay, so all together, we're going to add up the areas of these 4 rectangles for our estimate. And again, we can tell it's going to be an overestimate because it has a little bit of extra area in the corners, but it will have even less error than the 8 and the 5. All right, so I have my tiny rectangle first. Its width is, oh, sorry, I said 1/4. This should be 1/2. Its width is 0 to 1/2, so its width is 1/2. And its height is f of 1/2, which was 1/4. Okay, the next rectangle here, again, has width 1/2, not 1/4. And its height is 1. The third rectangle, again, its width is 1/2. And its height, we said, was 3/2 squared, which is 9/4. And then finally, the last one, also with 1/2, but its height is 2 squared, which is 4. All right, we could do this by hand, but why don't we pull out a calculator since the numbers are getting kind of gross? And we'll get an estimate here, or sorry, a computation. So I have 1/2 times 1/4 plus 1/2 times 1 plus 1/2 times 9/4 plus 1/2 times 4. All right, 3.75. So now I'm kind of inching even closer to the exact area, and I will spare you in this video, but you could keep going, right? Where you use, how about 100 rectangles, right? And you could kind of turn this into like a formula compute the area of all those 100 little skinny rectangles, and you're getting really, really close to the exact answer for the area, which was the green space over here. Okay, I'm going to do one more picture, which you can see reserved here. I'm going to choose a different way to set the heights of these rectangles. So in all of the rectangles I've done so far, I used, like, for each little sub-interval that I created, I used the rightmost option to set the height of the rectangle, right? So 0 to 1, I used the 1 to set the height. For 1 to 2, I used the 2 to set the height. Same thing here. In each little sub-interval, I used the rightmost point. Its y value created the height of the rectangle. And that kept giving us overestimates. So what if we wanted to do this differently, right? Like, there was no real reason I did it that way. So we could still break this into 4 even rectangles like we did here, but we could choose to use, let's say, the leftmost endpoint for each little subinterval, and then we'll actually get an underestimate, which combined with the over is actually really useful. All right, so if I'm going to do 4 subintervals again, I'm again going to cut a 1/2 and 3/2, or again, if you prefer 0.5 and 1.5, that's the same. But now for each subinterval, I will choose the leftmost x value to set the height. So let's start on the right side first. So my last subinterval is 1.5 to 2. So I'm going to take 1.5, go up to the curve, and use this to set the height of that rectangle. So that's 1. For 1 to 3/2, my leftmost option is 1. So I'll go up to the curve at 1 and use that to set the height of that rectangle. Same for the next, so that they all kind of have their top left corner on the curve. And that means for the subinterval 0 to 1/2, the height is actually 0. So there's just no rectangle in that spot. So this area, again, the width of each little rectangle is 1/2. So this first one is 1/2 times 0. The next one, its width is 1/2. And then its height is f of 1/2. So that's 1/2 squared, or 1/4. For the next one, width is 1/2, but now the height is 1 squared. And then the last one, its width is 1/2, and its height is whatever 3/2 squared is. Again, I'll pull up my calculator to do the computation for me, because I'm feeling lazy. All right, so 1/2 times 0 is just 0. The next one will be 1/2 times 1/4. That's that 1/2 being squared. The next one is 1/2 times 1. And then finally, 1/2 times 3/2 squared, which is 9/4. All right, 1.75. And we know that this is an underestimate. So what we've sort of created for ourselves is a little window, right? The exact area answer is somewhere between these two numbers. And if I used, 100 rectangles this way and this way, I would get a really, really tiny interval that the right answer is in, which is useful, and we're kind of getting somewhere with all of this. Okay, I'll stop it with the rectangles for this video. There's just one last thing I want to talk about before we're done here, which is the different types of sums that are kind of in this vein. So what we've been doing is called Riemann sums, because Riemann is the guy who came up with all of this. All right, so what we just did was right-hand sum and left-hand sum. So each of these is just like a policy for how to choose the height of the rectangles in one example, right? So you'll see examples that are like, okay, do a left-hand Riemann sum with 4 rectangles. So you'll cut your interval into 4 even little subintervals, and you'll use the left-hand x value to set the height of each one. So the left-hand sum, you're going to use the leftmost x value in the subinterval. So that's what we were doing in this blue example right here. So for each little subinterval, like 1/2 to 1, I said, all right, 1/2 is the leftmost option. F of that is my height. For 1 to 1.5, the leftmost option is 1. F of that is my height. So this was a left-hand Riemann sum. The ones in red were right-hand Riemann sums. So this is when you're using the rightmost x value in each subinterval to set the height. There are also things you can see here called upper and lower sums, where instead of always going to the far left or right x value, you would just choose whoever in the subinterval has the highest y value to offer. And then the lower sum is x with lowest y value. So if we look back at this example we did, this right here, this left-hand Riemann sum is also the lower sum, right? So in each subinterval, I picked the lowest possible point I could. And this is an upper sum because I picked the highest possible point I could. But if this function were like way curvier and it went kind of up and down a lot, then the upper and lower sums wouldn't necessarily match either one of these. They could be something completely different because, it might be, the point halfway through the subinterval that actually has the highest height. All right. The very last type of Riemann sum that we'll cover in this class is called the midpoint sum. So instead of choosing the leftmost x or the rightmost x in your little interval, you're going to pick the one that's exactly halfway. So you're going to use the midpoint x in the subinterval. So what that would look like in this previous example, let's look at this one here since the spacing is a little bit better. So if you were going to do a midpoint sum here with two rectangles, we would still split our interval into two evenly spaced rectangles. But then for the rectangle between 0 and 1 right here, I would use f of 1/2 to set the height. And then for the rectangle from 1 to 2, I would use f of 1.5 to set the height. So instead of the top right or top left corner of the rectangles kind of touching the curve, it would be exactly kind of halfway through right here. Yeah, okay, so that's it for this video. These are our types of Riemann sums, and we will pick up with this in class.